Hello guys, welcome back. So here we have another question on communication systems from GATE EC 2021. A message signal having peak to peak value of 2 volt, root mean square value of 0.1 volt and bandwidth of 5 kHz is sampled and fed to a pulse coded modulation PCM system that uses a uniform quantizer. The PCM output is transmitted over a channel that can support a maximum transmission rate of 50 kilobyte per second. Assuming that the quantization error is uniformly distributed, the maximum signal to quantization noise ratio that can be obtained by the PCM system is dash. Okay, so to understand this, we first need to know what is a PCM system. So PCM is pulse coded modulation. So suppose we have an analog signal. So you know that analog signal, when we transmit it, it's prone to noise and other stuffs. So what we do, we first sample it and digitize it. So here we can use like n equal to 5 samples, something like that. So for example, if this level is from plus v to minus v, I will divide this level into, let's say, this 2 power n levels, and then I will sample, and if it falls in any one of this level, I'll have the 2 power n values, right? N bit value. So I'll sample each one into a n bit value. So here it is an example, only 5 bit. So if it is 5 bit, so I'll get something like 0 0 0 0 0 0 0 0 1 0, something like this, right? So then I'll take this value and I'll code it in a pulse form. Code in pulse form. So what is pulse form? 0, I will say the level is low, and 1, I will say the level is high. So for 0 1 0 1 1 0, what will be my thing? It will be like this. So this is corresponds to one of my sampled points, right? So the next sample point will come here later, and the previous sample point would have come before. So I'm coding it in the pulse form, so it is called as pulse coded modulation. Okay, so this is the pulse coded modulation. So here what they are given about the input message signal. So it has a peak to peak value of 2 volt and mean square value of 0.1 volt. So we have message signal, peak to peak value is V peak to peak is 2 volts, and RMS is 0.1 volt. And then what they have given, bandwidth of 5 kilohertz. So F bandwidth is 5 kilohertz. And what we need to do, we need to transmit it over a channel that can support maximum transmission rate of 50 kilobyte per second. So channel as a maximum rate, which is also called as its capacity, right? So this is 50 kilobytes per second. And then the quantization error they are saying is uniformly distributed. Then they are asking the maximum signal to quantization noise ratio that can be obtained as dash. So we know what is quantization noise, right? It is the noise when we are sampling an analog signal and converting into digital form. The error made in analog to digital conversion. So how do you reduce this noise? So for signal to noise ratio, quantization signal to noise ratio, it is your power of signal by power of noise. To reduce this, what you have to do, you either need to increase PS or reduce your P noise, power of your noise, which means that you need to reduce your error. How will you reduce your error? You need to have more levels, finer levels, right? So you need to increase your N, increase your number of bits. So here what is limiting your number of bits? One is your bandwidth, signal bandwidth, and second is your maximum rate of transmission, right? So signal bandwidth is 5 kilohertz. So we want least amount of samples from here. Then what I have to do? I have to sample it at Nyquist. And what is that rate? Fs is equal to minimum Fs without losing any information. It will be 10 kilohertz. So now for each signal, I'll have only two samples, right? For each period of a signal, I'll have two samples. So by doing this, I'm minimizing the number of samples. So why I'm minimizing the number of samples? So I can maximize my n. So what is my n limited by? Your F channel max is 50 kilohertz. So Fs min is 10 kilohertz. I'm sampling at 10 kilohertz. So my n is limited to 50 kilohertz by 10 kilohertz. So my n is less than or equal to 5. Now I said I want to maximize my n. So I will always choose n equal to 5. Okay. So for n equal to 5, we can find the P noise, and then also PS we can calculate from its RMS value. So let us do that. So power of signal is nothing but your RMS square directly. So which is equal to 0.01. And then now we are coming to the P noise. So for a quantization noise uniformly distributed. So from minus delta by 2 to delta by 2. And this is 1 over delta. What is your noise? Your noise is nothing but the variance of this distribution. So this comes to be delta square by 12. So this is delta square by 12. For this case, what is your delta? It is your peak to peak divided by the number of levels, right? So here it is 2 divided by 2 power 5. So which is 1 by 16. 2 power 5 is 32, right? So delta is 1 by 16. So your Pn is 1 by 16 square into 12. And this is your minimum quantization noise. So now can we find our maximum QSNR, quantized SNR? QSNR max is equal to PS by Pn min, which is equal to, what is PS? 0.01 divided by Pn min is 16 square, 1 by 16 square into 12. So if you use the calculator, this comes out to be 30.72. And if you say this is not in dB, here in the question they haven't asked specifically in dB. So you should just leave it like this. If they have asked in dB, then you should take your 10 log into this. Why 10 log? Because it is in power. Units of power, it is always you need to take 10 log for power. For voltage and current, you can take 20 log. Because this power, already this quantity is having that square. So to keep the consistency as it is, here it is 20 and here it reduces to 10. Okay, voltage or current. And here dB is not asked. So no need to take dB. Okay. So the answer itself directly is 30.72.